thanks very much for having me and for hosting. I do realize I'm the last thing standing between you and dinner, so I'll try to stay on point. The work I'm going to be talking about today is a collaboration between me at the University of Texas, Dominic at Grab Technologies, and then a group of computational immunologists at Yale. And it concerns an attempt to model protein sequences in a different way than has been attempted previously. The structure of the talk is roughly this. So first I'm going to present some background material which builds up to our approach to modeling sequence and draws on some of our previous QI work. And then I'm going to sort of switch over to computational immunology and talk a little bit about that to the best of my limited ability. And then explain how we model proteins using the methods that we developed in previous QI contributions, and present an evaluation of these representations of protein sequences in the context of sequences gathered that represent an immune response to West Nile virus. Some of you may know it's a mosquito-borne virus that turns out to be quite prevalent in Houston, Texas, where I'm from. That's something of an accident that it ended up being that virus. So just by way of introduction, I know we heard about these in the last talk, but I'm going to start out talking about semantic vector representations, which are representations of words that are learned from large text corpora, usually by, as was said in the last talk, creating a sort of word by context matrix, sometimes reducing the dimensionality of those. In case you haven't seen these before, I put up a few examples of the sorts of things these learn. So I picked some words that came to mind during the course of the presentation this afternoon, and what you're seeing are the nearest neighboring vector representations in a distributional space to the vectors for those words. You can see we find words that are somewhat related to one another. Early on in the slide, I just mentioned some sort of famous examples of these sorts of distributional models. LSA is latent semantic analysis. HAL is the hyperspace analog language. Random indexing, which Penty developed, is another approach. And lately, neural word embeddings have become very popular as a way to generate these vector representations of words. In the work that led up to this work, we were trying to address two limitations of these models. The first is that they don't explicitly encode structure. I would have said they don't encode structure at all, but some of the evaluations of the word embedding suggest that they do sort of implicitly encode structural relations. But the other issue is that even though they're continuous representations, somewhat ironically, we're using them to encode discrete observations of words in contexts, right? So the consequence of this is if we see something that is numerical in the text, it's usually discarded. So often the numbers are just treated as a number or converted to a single number or discarded entirely, which means that if you run into 105 degrees in the context of Phoenix, Arizona, where it's the average temperature in summer, or has been, and you run into 106 degrees, which was at one point the average temperature in Las Vegas, you'd end up with representations for these two places that are dissimilar from one another, even though the temperatures are similarly unpleasant. The issue of encoding structure actually relates a lot to the talk that came just before this, right? So, and I guess also to the talk about Chomsky and linguistics and the notion that language has a hierarchical structure to it, and that we'd like these models to be able to encode the structure, but the standard models and the models I just described don't address that issue. They treat words in a sentence as bags of words without explicitly representing the relationship between them or the structural relationship between them. So this was raised as a larger issue as an objection to connectionist representations, famously. The notion was that these representations couldn't possibly support cognition, where cognition was thought to be symbolic and compositional in nature. So, and Smolensky's work, which again we heard about in the previous talk, was a step towards addressing this problem. So Smolensky showed that if your fundamental unit of representation is a vector representation, you can nonetheless achieve composition using the tensor products to bind a filler to a role or to a variable to a value. So for example, you might want to bind a vector that represents temperature, which would be a role, to a vector that represents 106 degrees, which would be the filler for that role. The necessary feature of the methods that are used to implement this binding is that they be somehow invertible, because if they are invertible, then you can get the information back out. Right? So you can have a vector that represents temperature of 106 degrees, and you can use the vector for temperature to get 106 degrees back, and the opposite way around. So we heard about the tensor product as a way to implement this. There are a number of other ways to implement this binding. They include pairwise exclusive OR, where the vector representations are binary vectors. So this is a system called the binary static code that was developed by Pentti Canova, who's in the room. I've underlined it not just because he's in attendance today, but because this is what we used for the work that follows. But there are other ways to do this as well. So Tony Plate proposed a method called holographic reduced representations that uses circular convolution, which is a way of contracting the tensor products. And Ross Gaylor, who I believe coined the term vector symbolic architectures as a way to describe these approaches.
Plate introduced it probably in 1993.
Yeah.
Yeah.
So he also has an
It really
implementation.
goes, yeah, way back.
So he's responsible for the name. Yeah. So we've experimented quite a lot with these binding mechanisms for two different ends. Usually the way that they're implemented is to use a role vector and a filler vector that are close to orthogonal to the other vectors in the space in a lot of the work that we've done. And the reason this is advantageous is that then they're unlikely to be confused with other vectors in the space. Right? They're close to orthogonal to all of them. There's a nearly near infinite supply of close to orthogonal vectors in high dimensional space. But in the case of the temperature example, this isn't desirable. Right? We'd like to have a vector for 106 degrees that's somewhere near the vector for 105 degrees, so that Phoenix and Las Vegas can be close together in space. So we've been experimenting with abandoning this constraint that the vectors be orthogonal, or deliberately making them not orthogonal. And the way we've been doing that is with an approach we've come to call the graded vector approach, where we pick two orthogonal vectors in high dimensional space and interpolate between them. So we can deliberately generate vectors a fixed distance apart from one another and then include them in these models.
Can you say what you mean by interpolate?
Yeah.
There's lots of ways of doing this.
Well, so this is essentially how we do it. So it's easier maybe just to put it. So we take some of one and less of the other, basically, and then normalize the result. This was what we originally used these for. So we thought it might be interesting to try to develop representations of words that capture orthographic similarity. So the similarity between how words look, or the characters they have in common, in positions in common. And the way we went about this was by generating what we called demarcated vectors, or graded vectors, a fixed distance apart, such that the distance between the vector representing the second position in a word and the vector representing the third position in the word was much the same as the vector representing the first and second position, but twice that. The distance between the first and third was twice that, so approximately. And we used this to generate role filler bindings for character positions. But the point I guess I'm trying to get across is that the vectors that represented the roles of the positions in the character were not orthogonal to one another, they were a measured distance apart. And when you do this, you end up with vectors where words with the same characters in similar positions will have similar vectors. And what I've showed you here is an example of a search in such a space where you can see that we're finding similarities between words that have characters in positions, and the similarity drops as these positions are distorted more and more. What we thought was interesting about this model was that it's very simple, but it captures the sorts of robustness to transpositions that people exhibit when they read language. And then last year, we had a paper, which was mostly through Dominic's effort, to generalize this approach further and use it to encode any continuous property into a representation of a table. So, so this is the generalization. So here what you're seeing is a way of generating a demarcated vector for any value between two extremes, where alpha and omega are the two orthogonal vectors in the space, and we're just finding the distance from the top and the bottom and using this to generate a representation of a number between two extremes. And once we have those, we can generate a representation for a row in a table where the field is represented with a random vector, and that's bound to one of these graded vectors to represent the value. So in this way we can generate representations of things like the year of birth for presidents, which are the example that we had, so that presidents who have similar years of birth will have similar vectors. So essentially what these methods have